This video contains the solutions to the partial derivatives practice problems. So here we're asked for the first order partial derivatives f sub x and f sub y for f of xy equals x divided by y. So the first thing we should do for this problem is rewrite this as x times y to the minus 1. If you remember from earlier calculus classes, writing fractions with negative exponents is often a good way to help us take the derivative in a much easier way. So f sub x, which is also sometimes written del f del x, is the partial derivative with respect to x, which means we're going to treat any variable other than x like it's a constant. So if we think of x times y inverse, if we instead think of that as y inverse times x, well, if y is a constant, then y inverse just means 1 over y, and so that's a constant too. And so this is a constant multiple, so the y inverse just sticks around, and we take the derivative of x, which gives us 1. So our derivative is y to the minus 1. And then f sub y is the same thing, except we treat any variable other than y as if it's a constant. So again, this is sometimes written del f del y. So if we again think of it as x times y to the minus 1, the x sitting out front, that's a constant multiple, so that's going to stick around while we take the derivative. And the derivative of y to the minus 1 is minus 1 times y to the minus 2, using our power rule just like we normally would. So that's going to give us minus x times y to the minus 2. Now we're going to continue talking about this same function, x over y, and now we want to find the second order partial derivatives and also verify something called Clairaut's theorem. So it's helpful to remember the first order partial derivatives that we already found in the first problem, and now we're going to find the second order partial derivatives. So there are 3 second order partial derivatives. There's fxx, and then fxy, which according to this theorem is supposed to be equal to fyx. So actually we're going to compute those separately. And then the last partial derivative is fyy. So let's start with fxx. What that means is the x partial derivative of the x partial derivative. So we'll sometimes write it like this, or we might also write it as del squared f divided by del x squared. But however we write it, all this means is that we're going to take the x partial derivative of the x partial derivative. Now the x partial derivative is y to the minus 1. And remember that taking the x partial derivative means that we're treating any variable other than x as if it's a constant. But that means that there are no x's in my x partial derivative, and so the derivative of y to the minus 1 is the same as the derivative of a constant, which is 0. Now if we do fxy, this means that we're going to take the x partial derivative and then the y partial derivative, which means that we're really taking del y of del f del x. So the letters switched order because here, when I say f sub xy, this means I take f sub x and then take the derivative with respect to y. But that's exactly what I'm doing here when I'm writing it with parentheses. Now, if you're worried about that being confusing, again, Clairaut's theorem says that the order doesn't really matter. If you do an x and a y versus a y and then an x, it'll always give you the same answer. But here we're just verifying it. So what we're doing is we're taking the y partial derivative of the x partial derivative. So this is the y partial derivative of y to the minus 1. Now remember, y partial derivative means that we treat any variable other than y as if it's a constant. Well, we don't have any of those other variables in this one, so we just take the derivative like we normally would. We get minus 1 times y to the minus 2, or just minus y to the minus 2. For fyx, this means the x partial derivative of the y partial derivative, which is the x partial derivative of minus x times y to the minus 2. The minus and the y to the minus 2 are constant multiples, and the derivative of x is 1, so this is minus y to the minus 2. And again, what we see here is that this value and this value are the same. So that is a check to Clairaut's theorem. Finally, for fyy, this is the y partial derivative of the y partial derivative, which is del y of the y partial derivative, which was negative x times y to the minus 2. The negative x is a constant multiple. The minus 2 comes down via our power rule, and we subtract 1 from our power, so we get y to the minus 3. So that's going to give us 2x times y to the minus 3, and that's our last partial derivative. So here we want what is actually a third order partial derivative, fxyx. So we're going to do this in 3 stages. We're going to start with f sub x, and then we're going to get f sub xy, and then finally we'll get f sub x yx. So starting with taking an x partial derivative. For 3x squared y, the 3 and the y are constant multiples, and we take the derivative of x squared, giving us 2x. For 2xy cubed, the 2 and the y cubed are constant multiples, and the derivative of x is 1. And then finally, the derivative of 4e to the x minus y, we want to think of this using the chain rule. So this is 4e to the u, and the derivative of e to the u is e to the u, multiplied by the derivative of u. In this case, we're taking the derivative with respect to x, so the derivative of x minus y is 1 minus 0. The derivative of x is 1, but y we're treating like a constant, and the derivative of a constant is 0. So cleaning this up a little bit, we get 6xy plus 2y cubed, and then minus 4e to the x minus y. All right, so now let's figure out f sub xy. We already did f sub x, so we're going to take the y partial derivative of the partial derivative that we just did. So the y partial derivative of 6xy, the 6x is a constant multiple, and the derivative of y is 1. The derivative of 2y cubed, well, that doesn't have any variables other than y in it, so we take the derivative like we normally would, giving us 6y squared. And then finally, the derivative of 4e to the x minus y. Again, think of that as e to the u. The derivative of e to the u is e to the u, multiplied by the derivative of u. But this time, the derivative of x minus y is 0 minus 1, because this time we're taking the derivative with respect to y. So x is a constant, and the derivative of a constant is 0. And y, the derivative of y is 1. So we get 6x plus 6y squared, minus a minus is a plus, 4e to the x minus y. Now the last step is to take one more partial derivative. Now we're taking the partial derivative with respect to x. The derivative of 6x is 6, just like it normally is. The derivative of 6y squared, well, we're taking the derivative with respect to x, so any variable other than x gets treated like a constant. Y is a constant, so y squared is a constant, and 6y squared is just one big constant, and the derivative of a constant is 0. And then finally, 4e to the x minus y, one more time. Think of that as e to the u, and the derivative of e to the u is e to the u, multiplied by the derivative of u, and the derivative of u is one more time, 1 minus 0. So our final answer is 6 plus 4e to the x minus y. Here we have a function of 4 variables, g of w, x, y, z, which means it has 4 first-order partial derivatives. G sub w, g sub x, g sub y, and g sub z. When we take the derivative with respect to w, anything that involves a term that does not have any w's in it is a constant. So that means that, as strange as it might seem, the sign of y minus c, that is just a constant. And so the derivative of this function is going to have the sign of y minus c is just going to be a constant multiple that hangs out. And then we take the derivative of cosine of w plus x. That's not a constant because it has a w inside of it, and the w is what we're treating like a variable. So the derivative of cosine of anything is the minus sign of that thing multiplied by the derivative of the thing. And in this case, the derivative of w plus x is the derivative of w plus the derivative of x, which is 1 plus 0. So that's going to be negative sine of y minus z times the sine of w plus x. Similarly, when we take the derivative with respect to x, again the sine of y minus z is a constant multiple. And again, the derivative of cosine of w plus x is going to be negative sine w plus x times the derivative of w plus x, which this time is going to be 0 plus 1. But that actually gives us the same formula, coincidentally, for our partial derivative with respect to x. Now we're going to take the partial derivative with respect to y. And now the sine of y minus c is no longer going to be a constant. However, the cosine of w plus x, that is going to be a constant because it doesn't have any y's in it. So when we take our derivative, the cosine of w plus x, that's going to stick around because it's a constant multiple. And the derivative of sine of y minus z, well, the derivative of the sine of anything is the cosine of that thing times the derivative of the thing inside, again using the chain rule. So we end up with cosine of w plus x multiplied by the cosine of y minus z. And the next one's similar. Again, the cosine of w plus x is a constant multiple. Again, the sine of y minus z gives us a derivative. That's the cosine of y minus z, multiplied by the derivative of y minus z, which is 0 minus 1. We're taking the derivative with respect to z, so y is a constant, that gives us a derivative 0. Z, the derivative of z, is 1. So we get minus cosine of w plus x times the cosine of y minus z, and those are our 4 different first-order partial derivatives. Finally, we can estimate partial derivatives using tables of values, just like we estimated derivatives in Calc 1 using tables of values. So the way that we're going to do this is we first find the point that we're talking about. In this case, we're talking about the point where x equals 2.2 and y equals 3.4. So here's 2.2 in the x direction, here's 3.4 in the y direction, so we're talking about this function value right here. And so since we're taking the partial derivative with respect to x, our partial derivative, del f del x, is going to be approximately equal to a change in f divided by a change in x. So that means that we're going to change x a little bit. And what we could do is we could change x a little bit in the positive direction, change x to 3.5, or we could change x in the negative direction. And if we make a different choice, we might actually get 2 different answers to this question. So either one of these would give us a valid estimate, but just because we have to pick one, I'm going to pick 3.5. So I'm going to make x go up a little bit to this function value here. So what's my delta x? Well, my delta x is going to be the difference between those two x values, 3.5 and 3.4. My delta f is going to be the corresponding f value, 5.191, minus the corresponding f value, 5.043. When we subtract, we get 0.148 on top, divided by 0.1 on the bottom. That works out to be 1.48. And that's our estimate for the partial derivative.